Welcome back, ladies and gentlemen. We're going to be taking a look at theoretical and percent yield. It's in some ways a very simple topic, so hopefully I won't drag it out too long. And it kind of ties into a lot of the things that we've been doing up until now with stoichiometry. You see, yield can mean a lot of different things. Yield could be, for example, a yield sign for cars, the triangle, inverted triangle. It tells you to slow down and let other people go first. Yield can also be that you surrender. Yield could also be what you make, the yield of your harvest. And yeah, English is weird, I know. Same word, three different meanings. But here's the thing. As you can kind of see in your booklet, we've seen how to balance equations, and we know how to use them and stoichiometry to calculate the moles of products that we make based on the reactants we start with. But we've been kind of making a pretty big assumption here. We've been assuming that the amount of products is exactly equal to the amount of reactants we put in. We've basically been treating all of the chemical equations like some kind of a machine, a perfect machine that you put inputs in and outputs come out the other end. Unfortunately, it doesn't work that way. Not all the time. Actually, almost never does it. Generally speaking, there's always going to be some kind of side reaction, some extra thing that happens off on the side that we don't really want. This is why, for example, medicine has side effects, right? Like if medicine only did exactly what we wanted, that'd be great, but it doesn't, because bodies are pretty complicated and there's a lot of different things that it can interact with. So what we're going to be dealing with here is that usually some fraction or percentage of the reactants that we put in do not turn into products. An awful lot of chemistry actually comes down to figuring out ways to make that yield a little bit bigger. People can get very excited in the organic chemistry field when they can manage to turn a 96% reaction to a 97% reaction. Well, heck, they get excited if they manage to turn 96 into 96.5. The reason for that has to do with the fact that it can be very valuable. If, again, you're trying to make, say, medicine, and the ingredients to start are thousands of dollars, a 1% increase could turn into literal millions of dollars of product, depending on the volume of what you're using. So, with that in mind, if we take a look here on our page, it says that there are some terms for us to consider. You've got theoretical yield, which is how much product will be made under ideal conditions. So, in theory, what should we get? We've got actual yield, how much product was actually made during the experiment, right? What we expect and then what we actually get, which is almost always less. If you get more, you probably did something wrong, or conversely, Nobel Prize. Finally, you've got percent yield, which is a ratio comparing these two values, the theoretical and the actual. Let's write these down. All right, so you're going to have your theoretical yield, your actual yield, and your percent yield. All right. Now, the percent yield is calculated using the mass of product. Why the mass? Why not the moles? Because, again, we don't have a machine that can measure moles, but we do have a machine that measures mass. So if I have a reaction and then I've got some, thing of product on my dish, I can go take it to the scale and mass it. I can't take it to the scale and mole it. I can mass it and then convert it into moles, but one way or another you have to do some kind of conversion. So chemists decided that the conversion we're going to do is turn everything into grams and then compare it afterwards. They could have said turn everything into moles, but they decided grams is what we want to go with. All right, that's their call. We just have to deal with it. Anyway, as it says here, the percent yield can be calculated using the mass of the actual product obtained and the theoretical mass of the product calculated using the balanced equation reaction, aka the stoichiometry. So in terms of what this looks like is that you're going to end up with percent yield is equal to actual yield divided by theoretical. And again, masses, and then we usually times it by 100 to make it a percentage because it's got a percent sign in front there. That's it. That's the basic idea. So we're going to do an example to make sure this all makes sense. And the example, I think, should be pretty straightforward here. All right, we've got what is the percent yield of H2O if 138 grams of H2O is produced from 16 grams of H2 and an excess of O2. So we don't even need to worry about the O2, really. So this example is building off of our very familiar chemical reaction. We have done this particular chemical reaction dozens and dozens of times. First things first, we need a balanced chemical equation, so we're going to have some 2's in front there. That should do it. So what they're telling you is that we produced 138 grams of H2O, and we started with 16 grams of H2. And I want to know the percent yield. So in order to do that, we need an actual yield and a theoretical yield. All right, well, we've already got an actual yield. That's this one, right? This is what we actually got. But we need to know what the theoretical yield is. Now, in order to get the theoretical yield, we're going to have to do some stoichiometry. Now, on the plus side, it's not very hard stoichiometry. I mean, hopefully not at this point. We've had a lot of chance to practice. So we're going to end up with 16 grams of H2, and we want to get moles of H2. Set up our conversion matrix equals grams on the bottom, moles on the top, because we want to get rid of grams, we want to get more moles. The grams for H2 is going to be 2.02 for 1 mole. We set that up, what are we going to get? It's about 8. 8 moles. All right, so far, so good. We have now done step 1 of a stoichiometry question. All right, step 2, technically, we have our balanced equation. Step 2, we convert to moles. Step 3, we turn moles of the reactant into moles of product. All right. We use a different color here. We're going to go with orange. We've got here, we're going to get rid of some moles of H2. We want to get rid of those. And it says here we got 2 of those for every 2 moles of H2O. Well, that's very convenient. 2 for 2. Very straightforward. I mean, what does this do? In the end, it just means that there is 8 moles of H2O. Almost wasn't worth doing, but got to be complete for the sake of an example. Finally, we got our last step. We're going to convert from moles to grams of H2O. And these grams here that we're calculating, these will be our theoretical yield. Generally speaking, the way it works is that if it is measured in some way, then it's going to be an actual yield or an experimental yield. Whereas if it is calculated with a calculator, it's theoretical. And the reason we say that is because when you calculate something with a calculator, real life isn't that neat. It isn't that tidy. Usually something goes wrong. Maybe you spilt some, or something else got in the reaction chamber, or some side reaction happened. So because it's not as tidy, you end up with slightly unusual effects. And that means that you always get slightly less. So here we go. We're going to get moles, and we want grams on the top. Now, this is water, so we know that one's 18.02, he says, and then quickly checks in his mind. Let's see, 16, 17, 18. Yes, good. Whew. Oh, that would have been bad. So 8 times 18, and what we're going to get is 144.16. I did it in advance. So we got 144.16. So there we go. This is now, right? This is our theoretical. And this was our actual. Now, as the equation tells us for this particular unit, actual divided by theoretical, that'll give us our percentage. All right, so we're going to take our 138, and we're going to divide it by our 144.16, and that should give us our percentage. We plug all that together, and we're going to get 96%. So this is going to be 96% efficient. And that's it. That's what theoretical and percent yield is. And for the most part, I think you can see it's pretty straightforward. The hard part is not necessarily in calculating it. The hard part is in making sure you get a high enough number. There's all sorts of things where you guys will do labs, especially if you continue to do labs in university. There will be labs where you will do 3, 4, 5 hours of work and you'll get a 2% yield if you're lucky. And that sounds horrible, and broadly speaking, it is. Nobody wants to waste that much time and make so little. Generally speaking, a product that low, something went wrong. But it also could mean that maybe it's just a very inefficient reaction, and you, the brilliant chemist that you will soon be, are going to need to find a way to improve it. Anyway, that is theoretical and percent yield. It is about figuring out how efficient a chemical reaction actually is. And I think you'll see that doing this whole calculation to figure out what could be is pretty useful. All right, I'm going to leave it there, guys. See you next time.